Okay, so today or right now we're going to be doing the part 2 of exam 2 review. I think I'm going to start with the mechanisms first. These are the mechanisms that I got on my test. I just changed the reagents and the reactants up a little bit. Yeah, so let's start with the Eli reaction, the Wittig's reaction. So, Wittig's, I think this is going to be one of your more difficult ones to learn, just because the numbering can get a little confusing. But if you do number, it'll help you like a lot with this reaction. So, okay. Something I want to point out with the Eli is the resonance structure for it. So if I draw my resonance structure for my Eli, I have 5 bonds to phosphorus. Phosphorus likes to have 5 bonds. What I can do is I can put my electrons from the double bond on my carbon to make it negatively charged, and the phosphorus positively charged. So then we know that our carbon in this case is going to be our nucleophile. Carbon, nucleophile. Okay. So I'm going to do this here. Let's see if I can draw it in a better way. No, yeah, that's good. Yeah. Let me redraw phosphorus. Compound. And I'm going to number only the things that are going to be reacting in my reaction. So I'm going to number oxygen as number 1, carbon as number 2. The other carbon is number 3, and phosphorus is number 4. And so again, carbon is going to be our nucleophile. So from here, I'm going to break my double bond and attack the electrophilic carbon. Can't have 5 bonds to a carbon, so I'm going to break open this double bond and put my electrons on oxygen. So then, actually, these electrons are going to be attacking my phosphorus and making a bond to phosphorus. Sorry about that. So now I have an oxygen bond to my phosphorus. My phosphorus is bonded to this carbon right here. Let me highlight this carbon right there. And my carbon from the carbonyl carbon is going to be attached to the Elides one, the Elide carbon. And we form like a box, right? So right now we form the base structure. We're going to have to add the substituents so that we don't forget anything for this reaction. So on 1, 2, 3, 4. Okay, so on phosphorus, I'm going to put my PH3, my 3 phenols. On carbon, the carbon that was attached to the phosphorus has a methyl group and an ethyl group. Methyl and ethyl group. And I believe we're good right now. Yeah. Okay, so this is a concerted reaction, so we won't take long on this mechanism because it's all going to happen at once. I know that the end product is going to be this right here. Methyl and ethyl group again, because it's like what we did for the reactions page. We cut off the oxygen, we cut off the phosphorus, and we attach these 2 groups together. So I know that this is what my product should look like. So that's going to help you pretty much do your arrows for this mechanism. Change my color. There we go. So there's going to be a carbon-carbon double bond. So what I'm going to do is I'm going to break this phosphorus off because we know that we don't have a phosphorus in this compound. So phosphorus breaks off. We also don't have that oxygen. So this oxygen is going to break off of my carbon and form a double bond to phosphorus. That was the concerted step. And then we have this product. And then I'm going to draw the byproduct of this reaction. You won't need to write this in your mechanism, but this was just so you could see like how the arrows worked for this reaction. Yeah, looks good. Then for this one, again, remember the chart. So like the primary amines are going to make amines. Secondary amines are going to make enamines. Yeah. And this is an example of what an imine looks like. Double bond, carbon double bond to nitrogen. And a carbon-carbon bond, double bond. One carbon away from the amine, right? That's an enamine. These are examples of simple examples of things. So then when I'm looking at this reaction, I know that I have a secondary amine. So then I know I should be making an enamine. We know that enamines have a carbon-carbon double bond and that carbon-nitrogen double bond. So then we should know what our product should look like. And I think that's the first step to every mechanism that you're going to have in this test. Draw your product out first, so like how you would with the little tricks that you learn, and then go through the arrows for the mechanism. So then the trick for this one, just for the reaction, again, cut off the oxygen. Take off your hydrogen. Everything should stay the same. And just attach these groups together. Let me put this in a different color. Okay, so this should help you with the mechanism, and now we can start. So for the mechanism, the first step is, I forgot to include the mild acid. But it'll have mild acid, and for mild acids, we can use acetic acid. So acetic acid is going to come in and protonate my carbonyl oxygen. Now you have a positively charged oxygen group, something that's going to make your carbonyl-carbon very electrophilic, meaning that it's easier for a neutral compound like the secondary amine to come in and attack the carbonyl-carbon. So that's exactly what's going to happen. Yeah. So, hydrogen comes into attack. You can't have 5 bonds to an oxygen, so I break open the carbonyl oxygen in order to make that nitrogen bond. So now I have a nitrogen. Let me put that away. I have a nitrogen with 4 bonds now, so it's positively charged, as well as a hydroxyl group attached to my carbonyl carbon. What was my carbonyl carbon? So right now we have a good acid and a base. So what we're going to see is an intramolecular acid-base reaction, also known as a proton transfer. So then in the proton transfer, your oxygen is going to act as your base, going to get the proton from the amine, and we're going to break this bond to make the amine neutral. So now your amine is neutral and you have a very good leaving group. Cool. Amine is neutral, have a good leaving group. And so what's going to happen here is, oops, did I mess up on this one? I did. I messed up on this part. I said enamine and I gave you an imine. Boom. Nitrogen. Good. That's what it should look like. Okay. So you still have a good leaving group and everything. The only thing that differs from the imine and the enamine is instead of the acetate coming to deprotonate, to deprotonate your amine, it's going to deprotonate the beta carbon. So this hydrogen right here is going to come off and form an elimination reaction. So my acetate right here, again, it's like what your mild acid was your catalyst for this reaction, so you're going to have to reform the catalyst. So then what I'm going to do, deprotonate this beta hydrogen, put these electrons on a double bond. You can't have 5 bonds to a carbon, so leaving group leaves. me check if we're good. Yeah, we're pretty good. And then the reason that I deprotonated this hydrogen instead of this other beta hydrogen is because when I form the elimination reaction, my alkene is going to be on a more substituted position. So if I had put the double bond right here, it would have been disubstituted. Whereas in the place that I actually did put it, it's trisubstituted. So a more stable product. Looks like we're good on that one. This is the last one that I got. So I always pretty much analyze like the starting reagents and everything. So I have an organometallic. We know it's going to attack carbonyl carbons. We just need to know if our carbonyl compound has a good leading group or not. It has a chloride on it, so we're going to attack more than once. So let me just write on the top. This is a strong organo, meaning it'll attack more than once if it has a good, and it does have this. So let me write this out. Actually, let me write my product first. So I know it's going to attack more than once. I think this was one of the harder ones to like already know your product with, and it usually does help to know like the products in order to write the mechanism and everything. But this one is one of the more difficult ones. I think just because I have had some practice with this, I'll know it. But for this one, I think it's best to start with the mechanism. Yeah. So I'll start with the mechanism instead of the bromine, magnesium, and okay. So this carbon right here is right next to a metal. The metal is positively charged, as it should be, right? Positively charged metal. You can't have two like charges right next to each other. So we know our carbon right next to our magnesium should act as like partially negative, should have like a partially negative charge. So then on this compound, our carbon should be our nucleophile. So then my nucleophile from this bond is going to come and attack my carbonyl carbons. Break the bond, break the carbonyl bond, and form a negatively charged oxygen with a new ethyl group. And you highlight the ethyl group in the middle column. Okay, so usually we would protonate already. So the second step is H2O, and you usually protonate, but you have a good leaving group. So then instead of finishing the reaction here, my electrons are going to come in, reform the carbonyl, and kick off the good leaving group. So my second step should look like this. Good. 1, 2. 1, 2. Yeah. Right. Cool. Okay, so then again, we have a stronger organometallic, so we're going to be able to attack more than one. So this is going to be our second attack. Attack comes from the nucleophilic carbon bond to the electrophilic carbonyl bond. Break open the carbonyl. We'll keep these colors the same. And highlight this in the color. There we go. And so we get another ethyl group. And so finally, our last step will be the protonation, and that comes from H2O. Protonate, raw. So notice how all of this stays. Yeah. I think the key to this reaction is also knowing whether it's a strong organometallic or not. So know that the organolithiums and the Grignard reagents are strong, whereas the cuprates will only attack once. So if this was a cuprate, it would attack once, and you would only have your leaving group leave. So again, that goes back to the reactions page that we did in the last worksheet. I think I'll do the IR next. The IRs, you're not gonna need to remember a lot of them because a lot of the things that we are gonna see on these are like the common, the obvious IRs. So we know a big broad peak is gonna be our OH group, right? And so the thin sharp peak at 1700 inverse centimeters is going to be carbonyl group. And I'll teach you the trick to the other one because the other one is, I don't think, one that was taught a lot of times to many people. So let's just start with those. Okay. I already noticed my big broad peak right here. I have a big broad peak right here, so I know that I'm going to have an OH. Okay, and that's common with a lot of them. We have OH and OH, so it can possibly be A or B. Then I'm looking for something at the 1700 mark, which is like right here. And we have nothing. We would usually have something like a big spike right here. So no carbon, no carbon. So we're thinking it's probably going to be A. I think it's possibly A right now. So I'm going to put an asterisk on it until we find out what B is. If I look at the second one down here, I'm thinking this is going to be B because we also see a broad peak right here. But there's something wrong with it. There's something interfering with it. And I think it's because of this carbonyl right here at the 1700 mark. So we know we have a carbonyl. We know I have an OH. I look back at my products or at my possible answers, and I see carbonyl right here, OH, so it's carboxylic acid, and I think this is going to be B. And just by canceling that one out, I know that this will be A, so I can take off the asterisk. So then we're done with these. I'm going to do these two. Okay, so I think this is like a big trick to know for your like amines is the fangs. So check it out. For a primary amine, you have two big fangs. Fangs like little fangs, like vampire fangs. So it's gonna be something like two fangs for every hydrogen. That's how I think of it. So like one hydrogen, two hydrogens. And then you have just a normal amine with three hydrogens on it. You're gonna have three fangs. One for every hydrogen. And then you'll have a secondary amine with only one fang. And these are going to be kind of obvious. So if I look at this chart right here, I see those two fangs. I don't really have to remember any of the IR spectra because these are kind of like, these are the obvious ones. So I see the two fangs. So I know that it would be like an amine with two hydrogens and whatever the R group is. I look back at my possible answer choices and I see that D has an amide group on it. Okay, so then if we get the amide group, we're good with the NH2. That's already something we found, so it's probably going to be D. But I can also like make sure that I'm right by looking at the 1700 mark. We have an amide, so we should have a carbonyl group right here. And that's exactly what we see at this point. Yeah. Carbonyl group. So we know this is for sure D. By elimination, I was able to tell that this is C. But another way that you would be able to tell is, again, find the carbonyl group. This means C double bond O. And then I looked up the IR spectrum for aldehydes, let me check. And it was around the 2,700 mark. But this right here is a CSP2 hydrogen. It's right here. CSP2 hydrogen bond. And the IR spectra for those will be all of these signals right here. Yeah. Yeah, so mainly by elimination, I got that one. That was like I think I got this one on my test, and that's how I found out that one. So it's the obvious things that are going to help you with the ion. The big broad peaks are going to tell you the OH. The thin, sharp ones at 1700 are going to tell you the carbonyl. I think those are the main things that are going to help, as well as bangs. There's always like little things to know for each of the IR spectra. I think those will help you. This one I got on my test. I made these, but wait, did I make these? No, yeah. Yeah, I made these, but I got something like this on my test. And so what they're asking you is to pretty much find all the reactants that are going to help you make each of these compounds, or amino acids. A, B, C, and D. So for A, again, identify what your product is. So in my product, I have an imine. Okay, I forgot to note that we have to start with a carbonyl as a reagent and then add on whatever we want in order to make this product, right? So I have an imine. We know that we make amines with primary amines. So we know in order to make this product right here, we're probably going to be using the primary amine. And again, by using that trick where you split it in half, you know that you're going to have a ketone compound and a primary amine. So here's my primary amine and my ketone that you would regularly use to make your imine. And then I, just to be safe, would put like mild acid. So make sure we get all those points right. Because again, it's just like this one over here, where you use your secondary amine and your mild acid. So make sure that you put all the reagents, solvents, catalysts, and everything. For this next one, we have an acetal. We know that in order to make acetals, we need 2 alcohol groups, two OHs, and a carbonyl. So then what I'm going to do is I'm going to put my carbonyl in place of where my acetyl carbon is. And I'm going to add 2 moles of methanol. See, I'm so bad at nomenclature. Methanol. This is all we need for that. OH methanol. Oh, and I'm going to put an acid in there. So I'm going to do H3O+. Because we know that the H3O+ is going to protonate the carbonyl oxygen to make it easier for those alcohols to attack. So again, put everything that you can just to make sure that you get your answer right. There's a lot of possible things that you can do for each of these. So I came up with 2 options for letter C. And I'm going to write each of them, but if you think that you found another one, you can ask me in like Grignard or whatever. So for this one, I kept everything the same, so you can make it really easy for yourself and just do like, did I do 2 carbonyl? Yeah. Okay, so good. Okay. So I did a carbonyl carbon group, and I did an elide. So P, H3, P, double bond, hydrogen, hydrogen. And again, if you were looking at it, you would cut this off, paste it together. So you would think these 2 hydrogens, or these 2 hydrogens are here. So that's like one way that I had thought I could make this. The second option was to just leave that double bond there, make a carbonyl where the oxygen was, and react it with lithium, aluminum hydride as step 1, and H2O step 2. That could have been your second option. And we know that it would attack one time with the hydride and then protonate, right? to make this compound right here. For this last one, I think the easiest thing to do here is to make the halide. So then to make the halide reaction, so I'm just going to do my benzene ring with carbonyl. I think this is acetophenone. This is acetophenone. That's crazy. Okay, so I'm gonna react acetophenone with my pH 3P double bond, and I'm only gonna do one methyl group. Let's check this out. One. Again, you would cut it off right here, attach these two together in order to get this compound right here. All in the little piece. See if I'm good with this one. Yeah, good with that. I'm going to do this one next. Let's see if I can move this over. All right. These are not too bad. Draw the predominant species of L-lysine at a pH of 7.2. So pH is 7.2. And they, along with the predominant species of L-lysine at pH of 10.2. Okay. All you have to know, like the trick for this problem is deprotonate. Anything with a pKa below desired pH. So the desired pH being 7.2 in this case and 9.5 in this case, right? So then see all my pKa's are here. Let me do for pH of 7.2 first. So anything below 7.2 is going to be deprotonated. The only thing that I see pKa being lower than 7.2 is 2.18. So then I'm going to keep everything else the same. I'm going to write species the same. And I deprotonated the carb. Wow, how did I forget that? NH3. Carboxylic acid group. Whoa. Okay. So that's the only thing I deprotonated just because the pKa was lower than a pH of 7.2, right? Okay. So then for this one on the right, deprotonate anything below the desired pH. The desired pH is 9.15 in this case. So then anything below 9.15 is going to be deprotonated. And I see that 8.95 will be deprotonated. And 2.18 will be deprotonated as well. Everything else is deprotonated and deprotonated. So for good. Yeah, everything looks good on this chart. So notice how we lost hydrogen, deprotonated it, and we lost the charge as well. So make sure that this one will have no charge when deprotonated, not a negative charge. Then I'll do the synthesis. The synthesis for this one, the synthesis that you're probably going to get on your test is probably going to be like the TMDS, TBDMS, CL with the protecting groups. So I'm going to do, I'll show you the first one just to show you some of the reactions that I'm going to use to make it, to practice some of the reactions that we can use. But the second one is what I think you're going to see on your test, where you would have to like use a protecting group in order to go through with your reaction. So let's do the first one. Okay. So think I would notice how this group right here is a lot like this right here. And so what I'm thinking is I want to add a carbon-carbon bond. So I'm probably going to use organometallics. So in some way, I'm going to use organometallic. And then this OH is directly bonded to my cyclohexane. So then I'm thinking I'm going to use a ketone as well. I just don't know. I think that my ketone is going to be on my cyclohexane, right? So I'm going to start turning this group right here into an organometallic. And the way that I can do that is I want to turn my OH into bromine. And so with that, I'm going to use PBr3. So OH turns into bromine, PBr3. Second thing I do is I want to make an organometallic. So I already have my bromine, and now I'm going to use my magnesium with an ether. The ether is just like the solvent in this case to help the magnesium go in between the carbon and the bromine. Magnesium bromide. Step 1, step 2, step 3. So I have my organometallic, and now we're ready to attack carbonyl. So what I'm going to do is I'm going to make my cyclohexane have a carbonyl on it. So then it attacks the carbonyl and it makes an OH as well as another carbon-carbon bond. Let's see if that's the end product. Oh no, it's not. Almost. That'll give me a negatively charged oxygen and a new carbon-carbon bond. And then we have one more step. Step number 4, being just a protonate. So I can protonate using H2O. And I can get my end product. This right here. Okay. Let me put this down here. For my protecting groups, it's important to know what protects what. So for carbonyls, things that can protect the carbonyls are like this right here. The 2 alcohols connect to each other with a tosylate or any kind of acid. So this is going to be your protecting. And to deprotonate this, I'm going to use a strong acid, so like H3O+. And so another one that we can keep in mind for a protecting group is the ones that protect the OHs. And for this, I use TBDMS, chlorine, in imidazole. You can't forget to put commas with the solvents in them or the acids with them, because you'll have points taken off. And the D protector for this one is T-bath. And these are also important structures that we want to know. And structures would be part 3 of this review. So for nomenclature. Yeah. These are just ones to keep in mind, and this will help you with this problem. Pause and do it now. Let me go through this real quick. So I noticed this carbonyl is going to remain the same, and this one right here is going to be intact. That changes, and I think that I'm going to use like a reducing agent in order to make this alcohol right here. So to go from a carbonyl or an ester group to an alcohol, I would reduce. So if I wanted to use a reducing agent, it would usually interfere with the carbonyl that we have on this side. We don't want that at all. So we're going to use a protecting group for sure. So I'm going to use the carbonyl protecting group. That's the one that you have to remember. Remember which one goes for which one. This is TSOH. So step 1. It will only protect, I believe it's only ketones and aldehydes. So using that, I'll protect my carbonyl. And that was our first step. Second step, we can go through with our reaction. So I think I want to use a strong reducing agent, so something like lithium, aluminum hydride, in order to reduce as much as possible and make that ester a primary alcohol. So again, let me count just to make sure that I'm not messing up anything. 1, 2, 3, 4, 5, 6. Count all your carbons. Can't drop any carbons. So yeah, we're good with that. Oops. Not ready for the protonation. On carbon number 2, I have that acetyl thing. And I'll have a negatively charged oxygen where my ester should have been. For step number 3, I'm going to protonate. So protonate using something easy like water. And I get my primary alcohol. And that's all I wanted with this reaction. But we still have the acetyl. So then what you're going to do is you're going to start deprotonating. And then for this, you have to know the deprotonation step as well. So for this one, it's going to be H3O+. Or as H3O+, deprotonates, and you have reformed your carbonyl and gotten your desired product. I think this was all for this, right? Okay, cool. Okay, we're done with this worksheet, and then we can move on to part 2. I think the best thing to practice on this worksheet is things like this. So this is for sure what I got on my exam. I think this was probably like, it was fun, but it was the one that required the most thought, I think, because these you have like little tricks to them, mechanisms you memorize, IR things you memorize. And the synthesis is a little bit harder as well, but you know what reactions to use if you just do some practice. But yeah, on part 2, I'll go over some of the structures you have to remember for nomenclature, and I think more of this type of questions. So I'll see you guys.